Hello, Science Lines. Hello. She says, wiping a snack off her face. I am Lara. This is Theory of Science. We are learning about energy. I try and make these lessons so that you can just drop in whenever you like and learn about IGCSE physics whenever you like. This isn't one of those lessons because we're quite deep in now. This is like our 7th energy lesson. So by all means watch it. I would love to have you here. But if you're a bit confused and you come across stuff that you don't understand, it's not you. It's just that we've been doing this for a while. We're also going to have to talk about gravity a little bit, which we did in the forces module, which a lot of you won't have seen, which is again totally fine. You're just going to have to force your brain to go, oh, it doesn't matter. You can just plug the numbers in. It'll be fine. Okay, that's what I'm saying. Right. Very quick recap then. We have been looking at how energy can be stored. Energy can't be destroyed, can it? It can't be created. All you can do is shift it from store to store. So we've talked about energy being shifted from like chemical energy stores to elastic energy stores, like if you stretch an elastic band. Anyway, I won't go on. We've also looked at how energy gets shifted from store to store by various pathways. Yeah, so we talked about this last week. For energy can be shifted from store to store mechanically by force, or electrically, or by radiation, or by heating. What do I mean by that? If you imagine someone's holding a spoon and therefore heating up the spoon, yeah? You got a spoon, you got metal, it's the room temperature, your body is warm, you hold the metal, the thing heats up, right? So energy is getting shifted from your thermal store to the spoon's thermal store, and the pathway would be heating by particles, right? The particles in your body, they're vibrating a lot. So they knock into the particles in the spoon, they vibrate more, and then those vibrations get passed out. Okay, right, so let's start putting some numbers to this, right? It doesn't really have any, there's no point talking about energy really without talking about numbers. Why scientists started talking about energy in the first place really was to be able to measure things, to be able to measure like how efficient machinery is and things like that. So there is an equation that you can use to calculate or to put a number on how much gravitational potential energy something is storing, for example. Like, well, maybe I shouldn't give you any clues. So there's an equation, right? Gravitational potential energy equals, and then there's 3 different things that you times together to get how much gravitational potential energy is being stored in the gravitational potential energy store. I just don't want to tell you it because I feel like some of it, if I have a little chat to you now, you will just get, right? So let's say, from the oceans lesson, let's say I've got a jar of jam, okay? So it's probably not new news to you that if I lift this jam up, I am shifting energy to its gravitational potential energy store. Is that okay? I am doing work, aren't I, against gravity. So I've eaten some food. I have now got tiny little particles of food stored in my body. When I breathe oxygen in, then the oxygen reacts with that food, remember? So oxygen plus, in this case, food, equals a chemical energy store. So if I breathe in, I can shift energy from my chemical energy store to this jam jar's gravitational store. Is that all right? You could say I'm shifting it to its kinetic energy store, but that's sort of just in the middle, isn't it? That's that's the pathway being a mechanical force. So energy shifts from my body to the gravitational potential energy store off the jam. Is that okay? So, there are 3 things that you can change which affect how much gravitational potential energy something is storing, right? Can you tell me any of those 3 things? There's something we can change about this jar of jam. Like I can just change it to make it have more gravitational potential energy in its gravitational potential energy store. That's right. There's like an environmental factor. How do I try and talk you into it? There's something I think that's quite obvious that you can change about this jar of jam, which shifts more or less energy to it, okay? So that's one of these things. One of the things we can change, which changes how much gravitational potential energy it's storing. There's another thing, which if you like space, you might get. Izzy B, exactly, yeah. How high is what I think is the kind of, the more obvious one, yes. So the higher something is, the more energy is in its gravitational potential energy store. Yes, but that can't be the equation for gravitational potential energy, can it? There must be other stuff going on. We know this. How do we know this? How you straight away you know it's not just gravitational potential energy equals height. It can't be that because the units don't work out, right? We know that energy is measured in joules and height in physics is measured in meters, and joules do not equal meters. They are not the same. So there must be some other things going on. Joules, the unit that makes the units that make up the joule are meters, but times something else. Yeah, if you like space, oh, gravitational field strength. Thank you. Yeah, exactly. This is where we start talking about something called like little g, acceleration due to gravity. We learned about it in our forces lessons. This isn't really their lesson to learn about it. I'm sorry, I know that's really annoying. I'll put a G here. But G is basically, and I will just go really basic because you learn about forces in the forces module. G is basically how much stuff is being pulled down to the ground, okay? So on the moon, stuff is being pulled down less. The moon is smaller, less massive, so it's got less gravity, you could say. G is smaller. So if I took this jar of jam to the moon, then even if it was the same height above the surface of the moon as it is now above the surface of the Earth, it would be storing less energy in its gravitational store because just the moon isn't pulling on it as much, right? And the other one is, you might get the other one? Like intuitively, picture a jar of jam on Earth, on a shelf. Can you think of something else you could put on the same shelf, on the same planet, same shelf, same planet, that would store more energy, would have more energy in its gravitational store than the jam? Mass! Izzy B, smashing it. Yeah, well done. If you're watching on catch up, by the way, I do try and ignore the comments because I know it can be a bit annoying. A lot of people watch on YouTube so that they don't get the comments that are on Facebook, but that's quite useful. Hopefully you were thinking about the same speed as Izzy B there, or she's helped you out a bit. Yes, these are the three things that affect how much energy is in something's gravitational potential energy store. There you go. Gravitational potential energy equals the mass of the thing times G times height. Now G on planet Earth is 9.8. I mean, the question might ask you about other planets, but you would need to remember that little g on Earth is 9.8, okay? Can you have a go at these questions? Can you have a go? I don't necessarily need you to do them all. The first question is designed to be sort of quite straightforward. And the second question actually is also supposed to be reasonably straightforward. The third question is for the people who can do the first and second question and are getting bored. And this one is designed to really make them think a lot. There's a few different ways you could do the third question. This is one of my favourite questions to do in physics, actually, because it's a sort of little puzzle and you need to look at it from a few different angles, work out what you can work out, what do you need. But anyway, have a go at these for me, please. So little g is 9.8. If you do physics at A-level, you'll learn that it's actually 9.81, but you only need to remember 9.8, okay? And newtons per kilogram are the units. So 1 kilogram on Earth gets pulled on with a force of 9.8 newtons. All right? Anyway, Wormy, the Theatre of Science mascot Wormy, who we do not see enough of. She parachutes to the ground from a height of 100 metres. So she was 100 metres tall, high, up, and now she's landed on the ground, so she's at 0 metres. If her mass is 0.2 kilograms, can you calculate the change in her gravitational potential energy, please? So you've got the equation up here. Change in gravitational potential energy equals mass times g, which is 9.8, times the change in height. So in this case, she was 100 metres high and now she's gone to 0 metres, so the change is just 100 metres, yeah? Next question, a cannonball of mass 8 kilograms is fired directly upwards and reaches a height of 15 metres. How much gravitational potential energy does it have at its highest point? So, at 15 metres, right? And the next one, which is the fun one, it has lost 392 joules of gravitational potential energy. That's not a nice way of phrasing that, actually. That's quite an old-fashioned way of phrasing that. I should have said it has shifted 392 joules of energy from its gravitational potential energy store. But here we go, it's too late now. By the time the owner of the cannon realises he's going to get bonked on the head, how high is the cannonball at this point? All right, I will give you a bit of time for that. Because it doesn't matter at all if you get these questions right. You're not doing an exam tomorrow, probably. What matters is the brain exercise. This is how I learned physics, was by being given sort of tricksy little questions like this and just getting the answer wrong. I forget how often I got the answer wrong. So many times. So I really am going to try and just sit quietly and let you make as many mistakes as you possibly can, because I know it's tedious and awful, but all the mistakes you make do fuse neurons together. And when I tell you the answer, you'll be like, yeah, and it'll be better than if I just told you straight away. I tell you what, I'll go and get some coffee, and that'll force me to not talk. You want me to eat the jam? Yeah, do you know, I really want to eat the jam as well. Yeah, I do actually. Okay, I'm going to pour myself another coffee and have a spoonful of jam. And then after I've done those things, we'll go through the answers. So there's probably nothing more disgusting than the sound of someone you can't even see eating. But I literally did just make myself some bread and butter. And I'm dipping it in jam, and it's the best thing that ever happened. And this entire business model relies on me just doing what you tell me to do. And it's worked so far. And I'm just going to keep doing it. I'm not using that horrible supermarket jam though. I'm using my crabapple jam, which is the finest jam available to humanity. Oh, so good. How are you getting on? I don't want to rush you. I really want you to have time to think about this last question from every which way. Someone on Facebook yesterday was saying that they don't understand it at all. So, are you okay with the fact that G is, to be really simple about it, because this isn't the forces lesson, G is how much Earth is pulling on stuff. Okay, so if you're working out how much gravitational potential energy something has, you're going to do its mass, which is whatever its mass is, times g, which is always going to be 9.8, times the change in height. So there's two different specifications actually. Two different sort of companies could write your exam, Pearson or Cambridge. Cambridge phrases it as change in height. Pearson just says height. So I thought we'd better get used to both. Should we go through the answer? I'll have one more bite of jam. Oh. Okay. Right. Feel good though. Still chewing. Okay. This is your fault. This is why I shouldn't have comments on YouTube. Let's look at Wormy. How's Wormy been getting on? Gravitational potential energy equals mass times little g times height, or acceleration due to gravity, if you like. So you just put the numbers in, right? Her mass is 0.2 kilograms. Little g is 9.8 newtons per kilogram. And her height, or change in height, is 100 meters. So the answer is, if you want to be technical about it, let's see. Are you okay with if you divide something by itself, it disappears? Yeah? Like 100 divided by 100 is 1. A billion divided by a billion is 1. So here we've got a kilogram, but we've also got something divided by a kilogram. So those kilograms cancel out. So you're left with a Newton times a metre, which is a Newton metre, but we know from previous lessons that a kind of cool nickname for Newton metre is joule, and you should write joule in your exam. But I think it's useful to know that if you get Newton metres popping out of your equation, then you've probably got the right answer. So the answer was, Wormy has shifted 196 joules of energy from her gravitational potential energy store. Okay, moving on. 196 joules, you got that? A cannonball of mass 8 kilograms is fired directly upwards and reaches a height of 15 meters. How much gravitational potential energy does it have at its highest point? Okay, at its highest point is 15 meters, isn't it? So check that they haven't done anything tricksy, like it's on a step that is 1 meter high, but they haven't. Okay, so our height is just 15 meters. So that's 8 kilograms, that's its mass. So there's no tricks here. We just need to plug these numbers in, and what answer do we get? Gravitational potential energy equals mass times acceleration due to gravity times height, which is 8 kilograms, times little g, which is 9.8 newtons per kilogram, times 15 meters, which is 1,176 Newton meters, which is 1,176 joules. Okay, I thought the next one was really tricksy. It comes down, and as it falls, it shifts a certain amount of energy, and you have to say how high is it after it has shifted a certain amount of energy. So what we're doing is what they quite often do in IGCSE exams is make you do a relatively straightforward equation to get an answer, and then use that answer in the next question. So let's have a look. So it loses 392 joules by the time the owner of the cannonball realises it's going to get bonked on the head. How high is the cannonball at this point? So I would definitely draw a diagram for this. I'd draw a diagram whenever, but especially if I was in an exam. We know that it goes from 15 metres to this mystery height, and while it's doing that, it shifts 392 joules of energy, okay? Well, what can we do? We know how much gravitational potential energy it's got at the top. We know the height from there to there. We know that amount of energy. Okay, we've got the mass still, and we've got G. And we know its change in gravitational potential energy, so we can use all those numbers to work out the height. Is that okay? Gravitational potential energy equals mass times little g times height. So we're looking for h, this thing here. So we need to rearrange this equation to make h the subject. So we can go move, what have I done there? So another way of writing that is that right? Yeah, of course, that's right, yeah. So to rearrange equations, here we want h on its own. So we're timesing by m and g on this side. So if you move things over to the other side of the equation, you need to do the opposite. So we're timesing on this side, so we need to divide on that side, okay? So if you rearrange that, which you will need to know how to do for IGCSE physics, you end up with h equals gravitational potential energy divided by m times g. And then we just plug these numbers in, don't we? 392 joules divided by 8 kilograms times 9.8 newtons per kilogram is 5 meters. Now, it is very tempting in an exam to go, oh, brilliant, they asked me for a height and I've got a height, so that's the right answer. But it's not, is it? It's not the right answer because you needed this distance here. But you've got the whole distance. It was 15 meters high and it's fallen 5 meters. So you know that it's got 10 meters to go. It's just the highest point minus 5, which is 10. Phew! So very well done if you got that. Very well done if you didn't get that, but you're not freaking out and you know that those things just take a lot of practice. And there's loads of past paper exams online that you can practice that with if you like. Okay, can we do the activity and take a little break from questions before we think about kinetic energy? So what I would like you to do, please, is can you get a piece of string or wool and a blob of blue tack or Play-Doh, and can you put the blob of blue tack or Play-Doh on the end of the string? That is today's activity. I hope that you enjoyed it. That's literally it. Sorry. We're making what physicists call a pendulum. A pendulum is a posh physics word for blob on a string. There we go. So we're going to look at kinetic energy in a sec, but hopefully you know by now that kinetic energy is like the energy of movement. Kinetic kind of means movement, and there's a relationship between gravitational potential energy and kinetic energy, or those energy stores, I probably should say. So I thought it might help to actually have a pendulum in front of you so that we can talk about it, which is, you know, kind of like a swing is a pendulum, right? So first of all, I've sort of already told you, if you get a pendulum and you hold it, let's say let's say parallel to the floor, so let's hold it just straight out, so it's got the potential to fall. What energy stores are involved when it swings? That's basically all I'll ask you first of all. If you hold it like that and then you let it go, what energy stores are involved? And what pathway is it? Energy is being shifted, isn't it? Is it? Is energy being shifted when you drop the pendulum? And if energy is being shifted, then what stores are you talking about? What store does the energy start with? What store does the energy end with? And what's the pathway? How does it get shifted from one to the other? Shall I put this on a screen for you to make it make a bit more sense? Here we go. What energy stores are involved when a pendulum swings from A to B, and what pathway is involved as well? How is the energy shifted from A to B? I've been super kind. I put some stores and pathways, or in fact all of the stores and pathways that you need to know on the screen. Have you got it? I think you've probably got it, haven't you? You got that? Where does the energy start? What store does it start in? And what store does it end in? What store does it end in? So hopefully you're saying, well, it starts quite high up. So it's got energy in a gravitational potential energy store, and then as it falls, energy is being shifted to a kinetic energy store because it's speeding up, right? It's starting to move. And the pathway, well, the clue's in the gravitational potential energy store's name. It's being shifted mechanically by a force. Indeed, the force of gravity. It's being kind of pulled down to the ground, unless you like Einstein, but we're not going to talk about that yet. Is that okay? So gravity, energy is being shifted from the blob's gravitational potential energy store to a kinetic store mechanically by the force of gravity, which is basically its weight. Okay, have a think about this then. At which point in the swing, and you can use your pendulum if you like, have a little fiddle with it, study it. At which point in its swing does the pendulum have the most gravitational potential energy? At which point does it have the most kinetic energy? At which point is it travelling fastest? And are there any points at which it stays still? So I've got you, let's say that this is you holding it, point A. This is you starting to drop it, or having just let go, is point B. When it gets to the bottom, as low as it can go, that's C. As it starts to go up again, that's point D. And as it reaches the other side, that's point E. At which point in its swing does the pendulum have the most gravitational potential energy? At which point does it have the most kinetic energy? At which point is it travelling fastest? And are there any points at which it stays still? And can you see a problem with my diagram? Can you see a problem with my diagram? Nice one, people thinking about chemical energy stores. Yes, when I picked up the ball in the first place. Yeah, you're quite right. Yeah, you've got to be really careful what the exam question's asking you in this case. Okay, well, hopefully at which point in its swing does the pendulum have the most gravitational potential energy is a fairly straightforward question. If you can answer that, then, and you've understood what we've talked about so far, you can answer the second question, even though it might really seem not obvious. And if you can answer the second question, you can probably answer the third question. And yes, indeed, there is a problem with my diagram. Nice. Yes, exactly. Someone in the comments pointing out that, yeah, E's too high, isn't it? What we've done is we've assumed, like a lot of physics problems is, that there is zero friction happening here. This is a completely frictionless pendulum, because yes, you're quite right. If it starts out with this amount of kinetic energy, it starts out this high, then yes, it is shifting energy to its kinetic store. But we know that basically whenever something moves, energy gets shifted to an internal, like thermal store as well. So as the ball moves through the air, it sounds weird, but it is going to be slightly heating up the air around it. So energy is going to get shifted to the thermal store of the surroundings. And whatever this is here, like if this is a swing, and this is where the swing's rubbing against the top of the frame, then there's going to be some friction. So the thermal store of the actual pendulum is going to, energy is going to be shifted there as well. So it's not going to have the same amount of energy at A as it has at E. So it would be slightly lower. Yes, you're quite right. Well done. Okay. Well, hopefully you said that it's got its most, and it's got the most, it has the most gravitational potential energy, if you like. Again, I'm not totally sure that the Institute of Physics would agree with that wording. Its gravitational potential energy store is fullest. The higher it is, right? We've just looked at that. Gravitational potential energy is affected by height. The mass of the pendulum and little g are staying the same. So the higher it goes, the more gravitational potential energy it's storing. So it's got the most gravitational potential energy there. If it's shifting energy to its kinetic energy store, then it doesn't feel intuitive, but you know that as it falls, it's shifting energy away from its gravitational potential energy store and into its kinetic energy store. So it's got the most kinetic energy actually when it's at the bottom. It's speeding up, and it's got the most energy in its kinetic store when it gets to the bottom. So the point that it's travelling fastest is also at the bottom, because that's when it's got the most kinetic energy. Let's give you these answers on the screen. Why do I bother to put these answers in nice little circles if I'm just going to tell you them? It's got the most gravitational potential energy at A. I've said at E as well, because it's a magic frictionless pendulum, but well done if you just said A. That would technically be correct, yeah. At which point does it have the most kinetic energy? That is at C. So that is also the point at which it's travelling fastest. And are there any points at which it stays still? Yeah, if you swing your pendulum, you might be able to see that there are brief points at either side when it just hovers in the air before it changes direction and turns around again. Okay, so let's talk about kinetic energy. I'm just going to tell you this one, because it's not quite as straightforward as gravitational potential. The equation for kinetic energy is half mass times velocity squared. So the speed that something is going in, basically, its velocity squared times its mass, and then times by a half. My brain would much rather it look like this. Wait, that was backwards, wasn't it? Sorry. But in the exam, they show you it as half m times v squared. So I have to show you it like that. But are you okay with the fact that if you times something by a half, it's the same as dividing it by 2? My brain much prefers that. Look at it. I can just see that. But anyway, sorry. Now, there's an important lesson for road safety here. Notice that v, velocity, or speed, is squared. So if v is 2, v squared is 4. If speed is 3, velocity is 3, v squared is 9. This is very important for road safety because if you're travelling along by school and you're going at 33 miles per hour, but the speed limit is 30 miles per hour, you might be like, it's only 3 miles per hour over, like what's the big deal? But the amount of kinetic energy that your car has is not increasing by just 3 or whatever, because the equation for kinetic energy, how much kinetic energy you have, you take the speed and you square it. So even just a couple more miles per hour makes a big difference to how much kinetic energy you have, which obviously makes a big difference to how much energy gets shifted if you, for example, hit somebody. So important road safety lesson there, kids, for when you're driving your cars. Right, a couple more questions then. And then we'll do a question that puts all these things together. Now, I have made a mistake here. It's not even like, oh, it's deliberate, it's tricky. No, it's just a mistake. I've talked about a cyclist and I've talked about a person on a skateboard. But with the cyclist, I've given you the mass of the cyclist and the mass of the cycle. And you're supposed to know to add them together. But with the skateboard, I haven't told you the mass of the skateboard. I've basically just messed up. Okay. In fact, do you know... Oh no, I can't change the question because you've got it on your sheet. You just have to add the masses of the cyclist and the cycle together, okay? But the question is poorly worded, and for that, I apologise. But have a go at these. This first one is designed to be reasonably straightforward. I should have just said a cyclist of mass 100 kilograms, okay? But I didn't. But the cyclist is 90 kilograms and the bike is 10 kilograms, so can you add those together to get the mass? It's 100 kilograms, okay? So can you work out how much this kinetic energy this cyclist has if their mass is 100 kilograms and they're travelling at 11 metres per second? It's not a trick, it's just to get you to practice putting stuff into your calculator correctly, please. The second question might have a slight trick in it. It might have. A 40-gram tennis ball travels at 30 metres per second. How much kinetic energy does it have? And this last one is a bit of rearranging for you. Again, just kind of putting things into your calculator practice. A 120 kilogram skateboarder has 2,940 joules of kinetic energy. How fast are they going? So you've got to rearrange that equation to find V for the last one. Forward a bit because my calculator has given up the ghost. I've got another one here. Oh, I think that's my calculator from college. Hopefully the battery's just low and I can replace it. So if I was you, I would put the speed into your calculator first and square it first before I did anything else. How are you doing? Hopefully you've done the first couple. If you've got the second one wrong, that's a good stage to be at. Before I go through the answers, can I go through it? Is that all right? Okay, a cyclist with a mass of, just add the masses together, I'm sorry, it was very unclear, and then you just plug the numbers in. So it's half times 100 kilograms times 11 squared. So you've got to do the squaring first because it's only the 11 that gets squared. So you end up with half times 100 times 121, which should give you 6,050 joules. Phew. That's how much kinetic energy is in the cyclist's kinetic energy store. The second one, did you see what the trick was? So again, there's no reason why you would know this really unless you'd seen previous lessons, which is why it's good that we mention it a few times. We've looked at how physicists have certain units that they use for certain things. Like mass is generally measured in kilograms, distance is measured in meters. Usually when you're doing equations like this, you've got to turn the units into those units before you crack on with the question. So for example, this ball is 40 grams. It's only 40 grams. How much kinetic energy does it have? Now, if you just put that 40 into your calculator, which is what I was trying to do, if you do 40 grams times 30 meters per second squared and divide it by 2, you get the answer 18,000. But that is not the right answer. You can't just stick, because you can't just stick joules there, because the unit, the joule, is made up of lots of other different little units, and it's not made up of the gram, it's made up of the kilogram. So what you've got to do is you've got to change the grams into kilograms, and then however many kilograms 40 grams is, put that into the equation instead. Here we go. If you don't quite get this, that's totally fine. You'll be learning this maths in your own time before you do IGCSE physics. Okay, here we go. So 40 grams, there's 1,000 grams in 1 kilogram, okay? So if you're going to change 40 grams into kilograms, it's going to be a much smaller number. There's 1,000 grams in 1 kilogram. So if you're changing just 40 little grams into kilograms, it's going to be a small number, right? So if you're dividing, then every time you move a decimal place forward, that's dividing by like a power 10. So this is how I do it anyway. I have to imagine the little decimal point after the 40, because that's where it would be, right? 40 is just 40.00000. So put a decimal point there. If you want to divide 40 by 10, you just move the decimal place forward one. And then you've got 4.0, which is right, okay? 40 divided by 10 is 4. If you move it forward another place, then you've divided by 100. So you imagine a 0.4 is 40 divided by 100. But we need to divide by 1,000, so you've got to move that point forwards again, and imagine a decimal point being there, and you've made an O appeared. So 40 grams divided by 1,000 would be 0.04 kilograms, which is what you've got. And then you just plug it into the equation. So it's 30 meters per second squared times 0.04 divided by 2. Please note that I made another mistake when I was doing this question. I put all that into my calculator and got 0.6 joules. And because I've done a lot of exam questions, and my brain has been trained to do this by my teachers who are very good, I always stop to check your answer. Always just take a moment to think, is that a reasonable answer? And I thought, that doesn't look right, that's a bit small. So I looked back and I realised, oh yeah, I forgot to square it. which is why you should write your working down as well. Okay, so finally I squared the velocity and I ended up with 18 joules. Whew, that was a lot of wrong answers to give you, wasn't it, before I gave you the right answer? Right, can we move on? Let's do the skateboardery one. A skateboarder, how fast are they going? Okay, now you've got to rearrange the equation. So if I'm going to rearrange this, the first thing that I'm going to do is write it out my way, because I like it written like this. So kinetic energy equals mass times velocity squared divided by 2. Right, so we need that V all on its own. So the first thing we need to do is, if we're dividing by 2 on this side, it means we times by 2 on that side, because we do the opposite when we move it over. So we can say kinetic energy times 2 equals mass times V squared. Let's get V squared on its own. Let's move the mass over there. We're timesing on that side, so we'll divide it on the other side. So now we've got kinetic energy times 2 divided by mass equals V squared. And then finally, we need to do the opposite of squaring here to get V on its own. So we need to do the same thing on this side, do the opposite of squaring on this side, which is square rooting. And now we can stick all that in our calculators. And we get the answer 7 meters per second. So this was quite nice, wasn't it? Like if you got 7 meters per second, that's quite a nice, neat number. And you probably knew that you were right. Whereas in an exam, the answer might be 7.124. And you just have to trust that it's the right answer or not by looking back and checking every time. Okay, chums. Right. I'm going to do something that I don't normally do. I'm sorry about this. One of the things that you might have to do in an IGCSE is, the thing that, I don't know, it's in my brain. I do find this really fun. You might have to combine the gravitational potential energy equation and the kinetic energy equation. Think about the relationship between gravitational potential energy and kinetic energy to solve the puzzle. So I've got 2 questions here. One of the questions we will do all together in a second. And the other question, if you want to screenshot it when it's on screen, or if you go to my website, then there's printouts for free on my website under the current IGCSE section. You don't need to print it off if you haven't got a printer, but it's just stored there. Or the one was on, this lesson is stored on YouTube now, so you can look at it here. But this is 2 good examples of how you combine these equations. So I'll let you have a little bash at number 1 and then we'll go through it. And number 2, we'll go through it next lesson. So here's your equations. Change in gravitational potential energy equals mass times little g. That's 9.8. 9.8. Write it down now. 9.8. You'll have to remember that. Times change in height. And kinetic energy equals half mass times v squared. So the last question that I'm going to ask you to do today is, a 70 kilogram man sledges down a 6 meter high hill. If the snow is frictionless, how fast is he going at the bottom? What? Love it, right? Come on. So you've got his mass, 70 kilograms. You know that little g is 9.8, or at least you do in your exam because you've revised it. You've got the change in height. So you've got 6 meters. But you need to know how fast he was going and how his velocity is over here in this equation for kinetic energy. So what are you going to do? What are you going to do? How is E higher than A? Because it's a PowerPoint and I just drew it like that. That's how. If I'd used AI, then it probably wouldn't have been like that, but I don't. Oh, you agree? I love it when you guys start talking amongst yourselves. Oh, I see. Maybe that's quite an old comment. Yes, you're doing having an excellent discussion about point E being the same height as A. Yes. I seem to have run out of comments. That's weird. Oh no, there we go. This is weird, right? Because you need to know his speed, and you might be thinking, okay, I've got his mass. Obviously, that's just a half. So I can just use this equation. But you haven't got his kinetic energy, have you? So there's two unknowns. You can't do equations when there's two unknowns. Is there a way of finding out how much kinetic energy he's got at the bottom of the hill? If the snow is frictionless. If you've already done it and you're getting bored, you can always like and subscribe, can't you? Oh, or, as always, over on my Facebook page is a Facebook post which says, if you would like to say hello, if like you can't log on to YouTube or whatever, and you can't like and subscribe and comment on YouTube, you can, if you've got a Facebook account, go to my Facebook page, and the very top post will be a post saying, please comment on this Facebook page. And I will go over there in a minute, in fact, when we've gone through the answer to this, and say hello to anyone who's watching. Hello, Bastian and Jacob and Casper and maybe Iris. Is that right? Hello, Liliana and Talitha. Should we go through this question? Oh, Madame Pomfrites, loving this lesson. That is so sweet. Okay, let's go through it. Because either you've seen how to do it by now, even if you haven't quite finished it, or you just sitting there like, just tell me. Okay, here we go. Well, what have we got? Well, what we need to know, what they were getting at, right, is the snow is frictionless, so no energy is getting shifted to the thermal store of the sledge or the snow. So the amount of gravitational potential energy he has at the top is the same as the amount of kinetic energy he has at the bottom. Just like our pendulum, right, is at the bottom. So all the gravitational potential energy was stored was shifted to the kinetic energy store. Once you know that, it becomes sort of reasonably straightforward, because if you work out how much gravitational potential energy he had at the start, then that is the same as the kinetic energy he's got at the bottom, and then you've only got one unknown, okay? So the amount of gravitational potential energy he had before he started sliding down this weird frictionless snow hill was his mass, 70 kilograms, times 9.8, which you've remembered is acceleration due to gravity on Earth, times 6 meters, because that's how high the hill is, which is 4,116 joules. Okay, so that's how much kinetic energy he's got at the bottom. So how fast is he going if there's 4,116 joules of energy in his kinetic energy store? Well, we know his mass, and we got the number for the kinetic energy, so we've got to do that complicated rearranging equation again. We've got to get V on its own. So we say that 2 times the kinetic energy, 4,116 joules, divided by 70 kilograms is 10.8 meters per second. Phew. Did you get that? So the first thing that I would be doing if this was actually a question was in an exam would be checking that my units matched what they wanted. So out has popped meters per second. If I go back, oh cool, yeah, I was looking for a speed. All right, so that's a good clue. Does that seem like a reasonable speed to be going? Well, I know that humans walk at about 3 to 4 miles per hour. That doesn't help, does it? I know that Usain Bolt can run at about 1 meter per second. So yeah, seems about right. And it is. Anyway, the second one I am going to let you do on your own, and then we'll go through it next week. A 200 kilogram roller coaster car has 21,560 joules of kinetic energy as it starts to move up a hill. If the roller coaster is frictionless, what is the maximum height the hill can be for the car to make it to the top? Phew. So have a little go at that. I thought it'd be nice for you to do something in your own time. And yes, then we will talk about it next week in our last energy lesson before half term. So it's been a big term, this one. We've done 8, we've done 8 lessons altogether, or we will have. So this was the 7th lesson, 1 more next week, and then I'm going to take, what you could call a break. I will be writing my science magazine that I post out to my supporters, and I will be planning my lessons. But it's a break from chatting, which is still a kind of break. Oh, look at these comments. Oh, Freya and Hannah are here. Splendid. Hello, you two. And there's Tim chewing the printout. Okay, Tim is a cat. It took me a second. Tim is a cat. Oh, Kai. Hello, Kai. Oh, and A is here as well. All right, A. E is slightly higher than A. Beautifully spotted. Yes. Is there homework for this lesson? We could do some extra practice. Oh, no. Freya and Hannah, I know. I've just... put up homework for the IGCSE lessons has become one of those things that is constantly second on my to-do list and never actually gets done. But actually, you asking about it makes me think, okay, it was useful to do it. I sort of thought it would be something that I could make and then it would just stay forever. But the links in it keep breaking. So last year, after every lesson, I would find loads of past paper questions and put them in a homework PDF for you. And then I thought I could use it again, but yeah, it's all just a bit messed up. And I was like, oh, it's a lot of work. I don't really know how many people are actually using it, but I will. It's on Coffee at the moment, isn't it? I'll just put it on my website like the printouts are. Every week that goes by, it gets harder to update it. Oh, hello, Joe. Didn't see you down there. Hello. Well, thank you so much for watching, you lot. I'm assuming that none of you are new. If you are new, then blooming well done for watching that. I mean, I suppose you're all at different stages, aren't you? Some of you might have revised in your own time. But if you do not know how these lessons work, then everything that I do is free. I'm trained to teach physics up to A level, but my lessons are free. The printouts for the lessons are free. I also do an all ages lesson, which is also free and kind of goes up to IGCSE level, to be honest. And a Lego show, which is not really a lesson. It doesn't go with printouts, just me chatting in a daft costume, but we all have fun and we learn some things. So if you think that is worth paying me for, then you can pay me £5 a month and I will send you some nice things, okay? Just go to my link that says coffee. If you're on YouTube right now, you can go to my about section. Wow, that pen is, oh look, this is what's been confusing me for months. Identical pens on the outside, but on the inside. I've got this website called Coffee. You go to it, you give me £5 a month and it funds these lessons so that I can do this job and I don't have to go and work in a school. So thank you very much for making it that I do this instead of working in a school. No one-to-ones. See you next week. Who I think is Casper. No one-to-ones, no private Zoom lessons. If you're watching this, you are my student. Bye. Thank you so much for coming, everybody. So yeah, thank you for paying your teacher so that I can continue to do this. I am going to go as well, and I will see you all next week. Bye.